Today, we're going to talk about why you need to pilot your machine learning systems, why just evaluating it on the test set is not really enough if your system is really critical, and why a test set performance might actually not be a very good prediction of how your model performs on real-world data, and why just reporting machine learning metrics might also not be enough to rebuild trust in your machine learning system. So in terms of our agenda, we're going to start at 9 p.m. for some reason, when we're going to talk about the test set and what a test set means, it meets the real world and how it actually normally ends up, which means that the test set will normally not be actually a very good predictor of how the model will perform in the real world conditions. Then we're going to talk, and then we're going to basically realize the need for pilots. Then in the second part, we're going to talk about how we can use the pilots and how we can evaluate them, gain useful, actionable insights about the actual machine learning system, whether it's ready to be deployed on the full scale or whether it still needs to be scaled back and reevaluated. Then we're going to talk about kind of an adjacent topic that is, I would say, essential to pilots, which is evaluating not only the machine learning metrics, but also the business KPIs. And then we're going to finish with a summary, where we'll basically say what are the most important key insights about running pilots, why they are needed, how to do them, and how to make them actionable. So let's start with the first part, which is the test set meets the real world. And unfortunately, real world has multiple issues that are not really well acknowledged and not well reflected in the model development process. So as we start to deploy the model, there's going to be additional issues that will pop up, and we need to make sure that those are addressed in one way or the other. And when it comes to deployment costs, there's kind of three kinds of costs that we need to take into account. First, sometimes actual deployment might be quite expensive. Because the models might be deployed locally, they might be deployed on-premise, or they might be deployed in multiple locations, which definitely increases the engineering cost and sometimes also human cost. If you need to deploy a model manually in a factory, that might mean that you cannot even do it in a remote setting, but there needs to be a human that does it for security reasons. Additionally, if you want to make sure that your model has actual business impact, that the recommendations or the predictions of the model are actually used in the real world, then more often than not, there is a significant operational change that is needed. Example here could be churn prediction, when the way that the retention team is working will have to change to accommodate for the predictions given by the churn model. And they will not be able to operate as they used to and still kind of grab the business value that the machine learning model could bring. So these operational changes generally are costly, both in terms of kind of human resources approach, when humans need to change the way they work, which is something that most people don't like doing. It takes time, so there needs to be enough potential business value to really justify that change. And the last thing is, for specific, really critical applications, like let's say reinsurance, a single false positive or a single false negative might actually have very catastrophic consequences, and we really need to make sure that the model is almost perfect, or in some really edge cases, really perfect in terms of not making one kind of mistake, but working with it making more of other kinds of mistakes. Another application here is medical field, of course, when we really want to make sure that we are potentially with a lot of false positives and detecting disease where there is no disease, but we want to make sure that if there is some kind of disease there or illness, we actually detect it. Then in terms of trust, domain experts quite often don't trust machine learning models, especially in more old school industries. So if you work in finance, that's probably not a problem, although it depends also what kind of finance. In insurance, it's probably a bit more challenging than in, say, algorithmic asset allocation or asset pricing. But if you work in manufacturing or some branches of medical field again, then the main experts often don't trust machine learning models. So we need to make sure that we can build that trust and that we can show that the model can be trusted in kind of objective way that's easy to communicate to domain experts. And then again, in some industries, leadership tends to overestimate human expertise compared to machine learning models, because human expertise used to be superior to any kind of rule-based system that they are used to. They're kind of, again, old school industries, or all their leadership people, they're generally used to these automated systems not working very well, which is generally speaking no longer the case. But the leadership still needs to adjust this level of trust they have in machines. And sometimes, of course, this low level of trust is very well justified, because you've seen a lot of kind of high-profile problems with machine learning models in production, especially with generative AI, which we're not going to be talking about today. But that is something that, again, potentially decreases trust in all kinds of AI, which ML is, of course, part of. And then if we actually experience early model failure right after deployment, that may significantly damage trust in the entire data science or entire machine learning team and in other use cases. So we really need to make sure that if we deploy something to production, it actually works on the first try. And that's why pilots are very needed, because then we can do something kind of sandbox environment when we don't risk that reputation of machine learning team, and generally automating and making things better with data. And then the last problem is adherence to procedures, that even if we manage to deploy something and we manage to change everything we need to change, we need to still make sure that whatever business process is supposed to follow model recommendations or predictions actually happens. Because sometimes people will still not follow model recommendations, even though they should, and even if we make sure that it's as easy as possible. And then kind of on the other side of the process, so kind of upstream from the model, sometimes there's lacking data collection, and as you already know, garbage in, garbage out. If data collection in production is not great, even if we have good model trained on very high quality data, if the data quality drops significantly after we deploy the model to production because the data in production was never good, then the model will not be good and will probably experience early model failure, which is something we really want to avoid. Now, another issue with real world is feedback loops, and specifically vicious circles. So now I'm going to walk you through a typical feedback loop that almost all models that are deployed to production actually experience. They are machine learning systems, they are dynamical systems, where model will act on the real world will respond in some way that will change the data that the model is consuming, and potentially will actually make the model worse. Here, one example would be that we make model predictions. The model predicts something. Based on that, we trigger real-world actions, and I'm going to give you a specific example in a second. Then these real-world actions will change the target definition or target distribution or something about the targets. And then we will retrain that model on different targets, which means that the model will be different. And if we change the targets, redefine themselves by the model acting on the real world, then the model will no longer be actually well suited for the use case. We're going to experience de facto concept drift, change in the concept we're trying to learn, even though we might not even realize it. Yes, that leads to model failure. Now, example here is going to be churn again. It's a very simple use case that I think everyone is familiar with. We're just trying to predict who's going to stop using some kind of recurrent service, such as using specific telecom provider or paying for Netflix. And here, the idea is that we make prediction who's going to churn from the service, who's going to stop using, let's say, Netflix. And then the real world action is that we send it to the retention department, and retention department works their magic. They do something to make sure that they return at least a part of the customers that were predicted to churn. That means that when we get the target, so we get who actually churned, the people that were likely to churn but were stopped from churning will no longer be marked as churners, which means that when we train that model on this new target and new data, the model will actually be trained to only predict the churners that cannot be retained, because the ones that were retained would be predicted as not churners. So we basically have a model that predicts something else now. And if we don't make sure that we really think through these real-world implications and this dynamical systems approach to models in production, we will not realize that the model is actually predicting something else that it used to. If we just retrain, and there's a lot of companies now that do automated retraining or retraining on schedule, and it might be that they're actually changing the definition of the problem without even realizing it. And now the model actually only predicts the people who cannot be retained. So then if retention will keep on using models predictions to target people who are potentially likely to churn, what will happen is that retention will stop working because they will only try to retain people that they were not successful at retaining before. The people that cannot be retained, that will change no matter what, which means that we will have increasing churn and the model will fail from the business perspective because it's actually a different model. The model is not useful because we don't really care about predicting who's gonna churn and cannot be retained. We care about predicting people who can be retained if the retention is focused on that kind of customer. So that's an example of a feedback loop, something that we want to understand and mitigate, but it's not something we can just avoid. And then in terms of how to do it, the best way to really kind of make sure that we take into account those feedback loops, apart from really trying to draw them out and see whether we should retrain and how we should retrain, how we should make sure that the model interacts with the world. Another way to do it is to have certain system of metrics that go beyond just our machine learning metrics, such as F1, ROC AUC, average precision. And then I'm going to just give you an example of few typical use cases and which machine learning metrics we should track, which business impact metrics we should track, and which guardrail metrics we should track. So to just drive a key distinction here, key performance metrics are basically the machine learning metrics we care about the most. So these are not all the metrics we could compute. These are the metrics that we really care about, that they are kind of a proxy for a business impact. It tends to be either F1, F beta score, or sometimes it's ROC AUC or average precision as well. If we just deal with probabilistic predictions for classification, for regression, it's going to be just your typical metrics such as MAE, maybe squared error or logarithmic error. So for predictive maintenance, there tends to be one single business impact metric that we really care about, such as mean time between failures. It might also be the uptime. And there will be some metrics that we also want to make sure that they are not above certain limits. We don't really care about them too much, but we put them in place to make sure that the model doesn't do something that's really stupid, that technically maximizes our main business impact metric. Imagine that we don't really care about the maintenance frequency for predictive maintenance, so we don't care how often the actual machines are maintained, as long as our mean time between machine failures, so as long as the machines don't fail, is fine. The best way to optimize that is to just maintain all the time, because then machines don't work and they don't break. So we need to have some kind of guardrail metric to make sure that this maintenance frequency is, for example, not higher than it used to be with manual maintenance schedule. For churn prediction, we can look at churn rate. We want to minimize the churn rate. That is the whole point of predicting who's going to churn, to stop them from churning. We can also look at the percent of predicted churners there who are actually retained. So we want to predict people who can be retained to avoid this kind of negative feedback loop I talked about before. And then for guardrail metrics, we can look at predicted churn rate. We want to make sure that not everyone is predicted to churn, because again, that makes model kind of technically correct, but not very useful. And we want to make sure that our cost to retain a customer doesn't just balloon out of proportion to the point when it doesn't make sense to retain them. And then for loan default, which is again like another very typical metric, I'm just focusing here on classification metrics and classification use cases, but you could also add here, for example, demand prediction. And here, typical business metric would be default rate. We want to make sure that the loans are not defaulted on more than before, or generally want to drive it as low as possible. But we also want to make sure at the same time that we accept as many loans as possible, because we want to give people loans, because that's how banks make money. And then typical guardrail metric here will be kind of weird because it's quite technical, but actually mean predicted probability, because this is kind of a good proxy for the default rate. And if it goes up really high, then we already know that something is wrong, even before we see that the actual realized default rate is potentially higher than it used to. So this is kind of like a proxy metric for the default rate, but we can use it as a guideline because it will allow us to figure out something is wrong faster. We don't have to wait for the actual defaults to happen. Now, kind of last issue that we have with deploying a models to real world is that we don't actually know what is the performance of a model. And this is super important because if we don't know what is the performance of the model, we don't actually know whether the model is failing or not. So we need to have something, some way to figure out how well the model is doing before we get the targets. And why is that? Because basically the targets always arrive too late. So typical kind of timeline of how the model works in the real world is that it gets its inputs, makes its predictions, then there's going to be some kind of business impact, can be reduced churn rate, etc. And after that happens, after people decide not to churn, we get it back in our database that this person actually has not churned, even though that person was predicted to churn, maybe because of some retention effort. So we were successful. So we get a target, but if something goes wrong with the model, then by the time we get the targets, then it's already too late. We already had negative business impact. Model has already failed. So we need to have a way to figure out what is the model performance before the targets arrive. And generally speaking, for any model, this is one of part of like something we specialized in. We have a couple of algorithms, both for regression and classification, that's focused specifically on performance estimation, when you can actually estimate model performance, estimate the impact of data drift on model performance, but we're not going to be focusing on that today. Today, we're going to be really focusing on how to evaluate model performance as part of the pilot, so we're not going to be talking about those algorithms. Now, in terms of missing targets, there's also one more thing to add, which is the targets are not only delayed, that they arrive later, but sometimes the targets actually don't arrive at all. If we, let's say, do some kind of document classification, we will never actually know whether the classification was correct or not, unless we do the job that the algorithm is doing manually again, which kind of defeats the purpose of the entire algorithm, because the point is to automate work, not to do it again. So we will never actually have targets for all the data points. Sometimes the targets are censored in a way that we will never know the actual target because the thing we do, the action, the business action that we follow up actually changes the target. If the person would have churned, would have stopped using a service, but we stop that person from churning, then the target is basically self-censored because the model acted on the real world. We did something with the prediction, and because of that, the target actually changed. So we will never know whether this person would have changed if we hadn't acted on it. So the targets are censored, we will never get them. And almost always the targets are delayed because we're predicting something in the future. And very, very rarely we get instant targets when we can just compute performance. Now, all these problems are there. How do we solve them? I think the most comprehensive solution is the pilot evaluation framework that we designed together with our customers. And it has basically three goals. First is to rigorously, hard word to pronounce, evaluate the performance of machine learning model in production. So we want to not only simulate production setting, but we want to actually put them all in production, see how it works in a limited way. Then we want to ensure that both the business KPIs and guardrail metrics are within specifications. Generally, business will have some kind of specifications for those. And so it's not only about the machine learning performance, but also the business impact. And we want to do it as fast as possible with as much certainty as possible. So we want to minimize the time to reach those conclusions. So again, here, we're not really making sure that the model is fit to be put in production. We are evaluating whether it is ready to be put in production. So we're really approaching it from scientific perspective. And if we say that the model is not ready to be in production, then we have to kind of go back to the drawing board and spend a bit more time on model development, business KPIs, guardrail metrics, etc. Now, we've defined the problem. We have the kind of high-level goals, kind of aspirational goals of the pilot evaluation framework. Now, how do we achieve those? So, in terms of how running a pilot works and evaluating the pilot works, it's as follows. we're just deploying a model in a limited way. We can do it in one location for one customer group, one group of machines. We're going to do it in some limited way that is representative of the actual production. So if we know that there is one specific segment that we expect the model to work really, really well on, we shouldn't do a pilot on that because it will not actually tell us how the model will perform on the entire population. We should get something that's representative of the entire population. And for example, just make the model predict on 0.1% of all the use cases if we have really good automation in place, or we can do it in one location or one country or one city. The way we do it is we're going to deploy the model. I'm going to skip all the part about how to deploy a model because there is already more than enough content about that. Then we're going to measure the model performance or estimate model performance if we don't have ground truth. We're also going to measure the business KPI when using the model, and we're going to measure the business KPIs when not using the model. So we're actually going to do a control test here, ideally randomized, but it doesn't really have to be randomized. If we have enough data, we get kind of automated randomization. I'm sure statisticians will hate me for saying that, but what the key point here is that we need to have some kind of control group that's ideally distributed the same way as our kind of treatment group, and where treatment is just the model being used in production. And then we're going to use the model pilot evaluation framework. When we will look at model performance, we will be able to see whether it performs according to specification, and we'll also be able to measure whether business KPIs when using the model and when not using the model are significantly different. Hopefully, the business KPIs when using the model are different and guardrail metrics are not deteriorating. So now I'm going to give you a kind of very brief intuition, maybe actually not so brief, about how the pilot evaluation framework works. So let's start with kind of let's start with a mouthful. So what we do is we use the HDI plus rope approach for Bayesian hypothesis testing to evaluate all the metrics in question. This is probably hard to understand for most of you. So to simplify it, the way we're going to do it is we're going to look at the distribution of the model before the model is put in production. We're going to also define whether based on the tested performance or based on arbitrary business decisions, we're going to define an acceptable level of performance. So that's going to be our red lines here, the vertical red lines, when we know that our accuracy is supposed to be between 0.85 and 0.82 and 0.85. We can base it on tested performance. We can base it on anything we want. Automatically, it's based on the tested performance, because if we are happy with the tested performance in production, then that's kind of okay, right? So the way we're also going to do it is we're going to calculate the estimated population mean of that metric. And we're not going to look at only at the mean, but we're going to look at the distribution of that mean, which is so-called the posterior in Bayesian statistics. And we're going to look at it and we're going to compare visually and also then mathematically the reference posterior, which is going to be mostly our test set, with the pilot posterior, the evaluation posterior, and we're going to make sure that they're not too different. The way we're going to do it is, well, first, we define the key performance metrics, so accuracy, F1, whatever we care about. Then we're going to define this region where we are happy with performance. It is called the region of practical equivalence, which is ROC. So kind of put a rope around a certain region, and we want to make sure that our metric is within that region. And then I'm going to start the pilot. And what you see here is this region where most of our posterior probability mass, which is called the highest density interval. So what you saw here is we have this distribution, and most of that distribution lies between these two, this point and this point, so lies within those dashed lines. And we're going to be drawing those dashed lines as we gather more and more data. And then we're going to be kind of evaluating whether that dashed lines, that region called HDI, just lies with our specified region of practical equivalence. And at some point, it will either fully go inside that region or fully go outside that region. If it's inside, we know it's fine. If it's outside, we know it's bad. Yeah. that's basically how we're going to conclude it. There's just one more thing here, is that we want to make sure that early, very weird results don't actually lead us to wrong conclusions. So we're gonna kind of enforce a maximum width of the highest density interval. Only after reaching that maximum width, and only if it goes below that width, we're gonna then start checking. This is done to make sure that very early unlikely streak of, let's say, very good model performance or very bad model performance doesn't give us a false result, either false positive or false negative result. We would conclude that the performance is fine when we just got very lucky, or that the performance is not fine when in fact we just got very unlucky. So to minimize the chance of that happening, we're gonna wait until our region of practical equivalence, or the highest density interval, of our posterior data is small enough. And here is an example of when we would accept that the model performance is fine. So we say that the model performance lies within the region of practical equivalence, and we can actually commence organization-wide deployment of the model. The model has been proven to work well in production. And in very rare cases, we will not be able to tell whether the model is actually within specified region of practical equivalence or not. These cases are rare, and then we can either continue waiting, or we can actually kind of adjust whether we're happy with potentially changing of what we consider to be acceptable or not acceptable. And then in terms of kind of concluding the pilot, we're going to look at each metric we really care about, each of our performance metrics, and then as we gather more and more data, our posteriors will change, they will adapt to new data, they will learn from new data, and also the highest density intervals of that posteriors will change. Hopefully they will shrink, and they will either go out or inside fully the rope, and then we can say whether we can kind of reject the performance of that metric or accept it. So here we see that the recall is accepted. We are happy with its performance, the performance of the model in terms of recall, but we are not happy with the performance of the model in terms of accuracy. And as for F1 and precision, we're still not sure. So that's how we evaluate model performance from the machine learning perspective. Now let's talk about business KPIs. The way we do it is kind of the same. So we're gonna define our business key performance metrics or key performance indicators. It can be, for example, whether people renew their subscription based on the churn model. So whether we actually successfully retain them, or it can be the actual churn level, or it can be the mean time between machine failures, or it can be the default rate, basically any of the key business indicators that we talked about before. The way we do it is we're gonna most of the time look at the difference between the actual business metric for our control group and our treatment group. And for some metrics, we'll be looking at making sure that it increases by certain amounts. So we want to make sure that our impact is at least that. So let's say that we consider a churn model successful if it reduces churn by at least 1% or at least 2%. And then we can just specify our region of practical equivalence to be between 10 and let's say 20%, because if it reduces more than 20%, there's probably something wrong with how we collect the data. So it's also a good kind of sanity check. Or in some business KPIs, we'll be focusing on making sure that it actually doesn't degrade that indicator. For example, when it comes to let's say a maintenance frequency for predicting maintenance models, we want to make sure that we don't maintain more often than before. We don't want to reduce uptime. And then we'll just look at the difference between those and make sure that it's not below 0. And then after we've defined that, we can start the pilot. We're going to be collecting data both from our control group and our treatment group, where treatment again is just model acting in real world. And we're going to collect the data, and we're going to again look at it from the Bayesian perspective, when we're going to be trying to find the actual true population value of the difference between those two groups. No, that did not work. Oh, yes. And the way you set it up, just a quick peek of how it works, is that you just put 4 columns actually, where you put the whether a given row belongs to a treatment or control group. Then you put the actual value of your metric, however, whatever metric you want. You can put as many metrics as you want, and then the data will be automatically collected from wherever it starts, and then we're going to evaluate it from the Bayesian perspective. And then in terms of concluding the pilot, it again is the same thing as before, where we'll just wait for reaching minimum or actually maximum HDI width. If it goes below that width, then we're happy to start evaluating results. And then we're going to start looking whether it's inside rope or outside rope. If it's inside, we say it's fine. If it's outside, we say it's not fine. And that is really it. So now, just to quickly summarize how we actually solve real-world issues with the pilot evaluation framework is as follows. In terms of deployment costs, we're going to be able to estimate the expected return on investment by evaluating business KPIs. And if they are higher than our deployment costs, then we deploy. We solve that issue. Then in terms of trust, we can let business fully define what is something that they consider practical equivalent and fine. So we're gonna let them decide what is the rope for some or maybe even all business KPIs and guardrail metrics. If they really want to make sure that certain metric doesn't decline, then we can just put it in the system and they will see whether that metric declines or not. And it's not something that we can control in any way, so they know that it is kind of objective, in a way, third-party evaluation. And we can also do the same thing for impact to make sure that we for sure have a certain minimum impact on the business. And that way we can actually build trust in the model because it's evaluated in a safe sandbox environment that really is real life production. So there's really no ways to make the model look better than it actually does, as long as we make sure that the way we choose our pilot data is representative of the real world. And you could say that it's kind of the same with the test data, but the main difference is that all kinds of human errors, machine collection problems, follow-up, adherence to procedures is going to be actually fully there for our pilot, but it's not there at all for the test data. And then in terms of adherence to procedures, if we see that the model performs very well, but our guardrail metrics are bad, then it probably means that there is a problem with adherence to procedures. So in other words, if we see that we see both model metrics within specifications and the secondary metrics or the guardrail metrics are fine, then we can assume that there is adherence to procedure, or at least enough. People adhere to procedures well enough for the model to still not create any issues and have enough impact. So we can assume that there is enough adherence to procedures. And in terms of solving feedback loops and missing targets, we evaluate business metrics, so not only the machine learning metrics. So there's some kind of feedback loop where it seems that the model actually performs well, but it's actually solving a different problem now and it's predicting a different target. This will be fully visible in the business metrics because, again, coming back to the churn example, the churn would increase if we did this simple or naive retraining that actually changes what we're trying to predict, and we would be able to catch it with our model evaluation framework. So if we don't see it, it means that there is no negative feedback loops. We also evaluate guardrail metrics, so if there's some weird feedback loops that are happening, but they don't really impact the key business metric easily, then we still also catch it with guardrail metrics. And then the last thing is that we can get these metric estimates with our performance estimation algorithm that we then feed to the Bayesian statistics engine, even without targets. So we can actually run a pilot even if our targets are censored or not available at all, or very strongly delayed, and we are able to get some kind of robust estimation of model performance without the target data. And then just to summarize the pilot in general, they're essential to build trust with stakeholders because they show that the model actually doesn't only work on paper, but works in the real world in a way that allows also them to have a say in what gets evaluated and how it gets evaluated, and what is the expected impact, and what are the metrics that they really care about. It is done in a safe environment, so even if something goes wrong, then we can just say that indeed there are issues and we can work on addressing those issues instead of dealing with actual fallout from very negative, potentially catastrophic failure of a model in true full-scale production. And then kind of from more statistics or machine learning perspective, we're combining our performance estimation algorithms with Bayesian statistics, and that gives us robust and interpretable results. Even if we don't have target data, we know what is the expected level of model performance and where that most likely true model performance actually lies.